Welcome to the first video on the Dirac field. We shall take the field the way it is presented to us and write up the Lagrangian, apply Noether's theorem and see what happens. So it's a question of making a model, the Lagrangian density, and applying Noether's theorem, and just take it as it comes, sit back and enjoy the ride and see what is the physics of this field really. So that is the first video. What is presented to us is often something about these lines. I wrote this up out of my head. I have seen things like it, but maybe you have only seen things, something like it. Psi, the Dirac field, is a four-component field, so the coefficients lie in the complex field, so at each point it lies in C4. This should give a real scalar, so there should be some inner product to this vector space C4, and that's of course always assumed to be the usual unitary inner product. Then they have the gamma, which is a vector of 4 by 4 matrices. And it's apparent here that they form a vector because this is the usual coupling between the gauge field or the electromagnetic field and a vector field. The next thing we find is a note that the invariant bra is this or something to that effect. Take for instance this book by Peschkin and Schröder. They explain it pretty well, but I think one has to know it well in advance to understand what they say. And in the section about free particle solutions of the Dirac equation, they say, we saw above that's on page 47, that product is not Lorentz invariant. Therefore, we define. And then they define something which is equal to this. I have some issues with it, but we have to take it at face value and say, okay, so we are not using the usual inner product. And there is a very, very good reason for that. You see, there exists no unitary four-dimensional representation of the Lorentz group. We should have a representation of the Lorentz group. And the boosts, if they map to a unitary group, then all the boosts are mapped trivially to the unit. And the usual representation that is presented to us, there they come out as non-zero matrices, which are not self-adjoint, by the way. I propose we embrace that and say, okay, the space we are operating now then is not the unitary space, but if we have two vectors, A and B, then the scalar product is given by this. And what I am doing is just taking gamma naught seriously and saying in the standard representation it's 1, 1, minus 1, minus 1. So that's what we get. This is a scalar product, not an inner product, because it's not positive definite. And it will turn out that the representation actually works in this space. We'll see it in a while. That's the first correction. that we actually work in this vector space. Then this is just the scalar product. And if we take A out from here, then this should be a real vector field. Therefore, the gamma vector need to consist of self-adjoint matrices. And of course it must be Lorentz invariant, but I presume you already know all about that. The next thing is that here we have a differentiation, and this is how they wrote it at the turn of the 20th century. One was always making geometry, writing out the coordinates. That's not how we do it today. This is simply the gamma vector doing its magic on psi, differentiating the directional differentiation of psi. So it can be done somewhat simpler, just psi and then the scalar product with the rest. And then that's just written gamma psi. I mentioned self-adjointness. I believe the space could be written this way. So it's 4 components and 2 are added and 2 of them subtracted. That's like the same way we write the Lorentz geometry. We need to know what the adjoint is. Adjoint operator, we have a linear operator A, and the adjoint is defined so that this relation holds for all psi and phi. It's easily solved. Here's the solution. This is a 2 by 2. They are all 2 by 2 block matrices. And to take the adjoint, we take the adjoint of them all. They map directly. They must of course change place, but then they also change sign. So that's how the adjoint is found. And I write up the gamma vector here. The matrix is not because I think they are new in any way or need refreshing, but just to rejoice with you in the fact that they are self-adjoint under our new scalar product. This of course is This is an adjoint vector matrix, and when it moves up here, we change sign, and that's what we do. This is an adjoint, self-adjoint vector, and when a matrix, and when we move it up here, it changes sign, and so does it. So gamma is a self-adjoint operator. Next, the representation of rotations and boosts. You may find this, and it's also presented in the book here, how to find them. So all the data are there. So I just applied it and found the boost, and then I realized that they move the coordinate system and not the states. I like that better when presenting the theory, because it's easier to think the way that we have one definite state and then observe it from different coordinate systems and moving coordinate systems, rotated coordinate systems. That makes more logic. But when applying them to states, as I want to, that's what I always do, then we have to change sign. Say if we have the spin-up particle at rest, 1.0.0.0, and want to boost it, then we get hyperbolic cosine zeta halves 0.0 point plus hyperbolic sine 0.0, because it's the particle we are boosting. And we can see that these guys are self-adjoints, SZ and BZ. and this is an error, down here it's a mistake. These guys they are unitary matrices, and we actually I actually want you to check that, and it's easily done. If we take the adjoint, then this guy is of course self-adjoint, and when it moves up here it becomes plus, and that's exactly what we get when we change sign on zeta. So it's quite clear that these guys lie in the unitary space with our new scalar product. And of course the determinant is 1 because they lie in the principal component of the Lie group. So it's SU 2.2. And sorry about that here. Now we are ready to look at the Lagrangian. The March term and the electromagnetic term come out as I said it. First the pairing of the gamma vector with the A field, and that's scalar, it's a matrix operator, just operates on psi, and then the scalar product of that, and the same with the March term. Now the self-interacting term here, I don't think it's explicitly real, or rather I don't think it's real at all. Now if psi is real, then this might come out imaginary, or some components, some parts of it imaginary. So I would like to force it to be real, and the way to do it is to take this part and then symmetrize it. We just take the complex conjugate and divide by 2. Then we can take the imaginary unit out and get this. Or we can reduce it from here just to being the imaginary part of this, and then with a minus. I like this very much because it's explicitly real. But I like this even better because it's more easy to differentiate. So we end up with this Lagrangian, where the scalar product is defined as I already did. That was the creative process. From now on, it's sit back, enjoy the ride, just let Noether's theorem do its magic. First, gauge invariance. That gives us the charge current density. Then translational invariance gives us the stress energy tensor, from which we can write up the energy, or as usual neglecting the Lagrange density, and the momentum density. That gives us 5 conserved quantities. To check the physics of the field, let's try and look at the planar waves and then subject it to Klein's paradox. That's always instructive. You've probably been told that it cannot be solved, but of course it can. We have Noether's theorem to guide us, so if something goes wrong, then it's the mathematician's fault, not mine. So it should be all right. The free planar waves. So I have boosted a particle at rest, and the energy is given by the usual formula and momentum. I prefer using the hyperbolic trigonometric functions when dealing with boosts. Just like when we're dealing with rotations, we'll use the usual trigonometric functions. And insertion gives the charge current, the charge density and the current. And this guy divided by rho gives the velocity, which gives the right result. And that's as it should be. The energy density comes out this way. If you divide it by the particle density, then you get energy h bar omega per particle, as we should, and the same with the momentum. So this is as expected from the non-relativistic theory. And of course we get the right velocity because everything was Lorentz invariant. That looks nice and was as expected. But now we come to the antiparticle, and that's where the fun starts. First, the charge density. I haven't put Q on any of this. It's actually a mistake. It comes out larger than or non-negative. So the field we have defined here actually has no negative antiparticles. So let's call this a measure instead of a charge density, because it can't be negative. So it's some kind of measure. Should we call the integral over the space for presence? So here we have the measure of presence. So we have presence conservation in this field. And you know what I'm hearing? From an ivory tower not far from here. They are shouting that I haven't understood that antiparticles move backwards in time. Actually, I have understood that, and very well. In the next video, we shall look at Feynman's adage, deconstruct it, and make a theory to I think I could say that it implies what he tried to solve. You may not like it, but at least it will give us a theory that represents the particles that we know in this universe. But if you change any sign or all the signs on these conserved quantities, what you're doing is actually ruining charge conservation, energy conservation, and momentum conservation. The theory you're making that way is faulty. We won't do that. We'll just apply Noether's theorem, be happy with it, and say, okay, that field doesn't seem to be represented in our universe, but we won't lie and change it. Right. The next step is to analyze the physics a little more by considering Klein's paradox. In the first one, I have chosen the incoming particle having a rapidity of 0.5 and the outgoing rapidity of 0.8, and I put k up here, and that was actually silly, because when k comes out positive, then we know the momentum is that way, so the wave will actually move that way. Silly me, but let's look at it. We have an incoming wave, and a larger outgoing wave, like 40%, 50% greater. And then there's an incoming wave. It generates an incoming wave this way. You may take a break, stop the video, and try to make sense of this and answer to your own satisfaction. What is the physics? What's going on here? I can just tell you, well, we have presence conservation. The flow of presence is continuous across the boundary, and we'll look at energy conservation later. This is the other example where we have an outgoing wave here, and eta is minus 0.08. Then the reflected wave is smaller than the incoming wave. I see I should have had a minus here, which is another mistake. We have an incoming wave, a reflected wave, and an outgoing wave here. That's actually more easy to understand. It appears that only about 2/3 of the wave is reflected. The last third continues within the potential. And now it should be easy to get the idea it's an antiparticle. So it has actually transmuted into an antiparticle with a larger momentum. So it has a larger negative energy, the negative kinetic energy, add the potential energy, and it just equals the energy of the incoming particle. Going back to the first example, here we have two incoming waves, and the outgoing wave is simply this one reflected plus this guy. What has happened is that the antiparticles coming here with all their negative kinetic energy, they have so much potential energy that their total energy becomes positive. They are therefore able to, when triggered to it by this field, to transmute into particles. Weird physics, but that's the legacy field we have. We need to change that, and that's the object of the next video.